Okay, so today we have the pleasure of having Antonio Mezzacapo. He got his PhD back in 2015 at the University of the Basque Country, and then joined IBM as a postdoc. And pretty recently, in 2022, he became the principal research scientist for IBM Quantum. So today we have the pleasure of having him give a seminar about merging HPC and quantum computers. So please, Antonio, go ahead.
All right. Thanks, Mark, and thanks everyone for joining this seminar. Thanks for the invitation. Let me share my slides. You should see the slides, right?
Yes. Yeah.
Okay, so I'm going to tell you what we are working on in the context of what we call quantum diagonalization methods. And this term is borrowed by what people like classical computing people call exact diagonalization methods, right? Except that we are using a quantum computer this time, and these are approximate diagonalizations. And so you see on this slide we have the IBM superconducting quantum processor here. And we have two supercomputers. One is the supercomputer Fugaku at RIKEN, and the other one is supercomputer Frontier at Oak Ridge. And this is the facilities, the supercomputing facilities of our partners RIKEN and Oak Ridge. And the results that I'm going to show you were obtained using our quantum hardware and in classical computing from our partners. Now you can see the reference. I'm going to talk about three works, and the reference you can see them here in the bottom right side of the slide. All right, so I'm going to talk about ground state algorithms, and I like to give a motivation. Well, algorithms for ground states are fundamental for many use cases in quantum chemistry and material science. And the goal, the motivation is, the belief is that using quantum computers will be able to do faster, better, cheaper computations that will be relevant for these domains. And obviously the development of new materials, new drugs, they're all related to how efficiently we can solve these computational problems. All right, so quantum computing has, holds this promise that some algorithms executed on quantum computers could be advantageous with respect to classical ones when tackling ground state problems. Now, if we look at the historical methods, right? So what existed before, but basically there's I like to think of there's two flavors of methods for ground state problems. One is the quantum phase estimation class, or derivatives, variants, or algorithms that use this as a subroutine. And so these are great, but they're very general, and they have some convergence guarantees. But the issue is that the depths, the circuit depths needed to execute this type of algorithm is very high, and so we can't really run phase estimation for realistic problems on the devices that we have today. And then on the other hand, we have witnessed the rise of variational quantum algorithms in the last decade. And so the idea with VQEs or VQAs is that they're also very generic, and you can get away with not so deep quantum circuits, so shallow depths, and they can be run. It's relatively easy to run small scale experiments on the devices that we have today, right? But what are the issues? The challenges with these methods, as I said, quantum phase estimation-like methods. We don't have the depths required to run these circuits today. And the main challenge with variational quantum algorithms is that, well, besides the fact that there's no convergence guarantees, the issue is the number of measurements required to resolve the landscape, the cost functions, the energies that we're trying to minimize is prohibitive if we consider realistic formulation of nature. Okay, so we have to come up with new things. But before showing you the new things, let me put some numbers behind this motivation. All right, so let's see really like what is the price of running like a VQE on a realistic molecule. All right, so let's take Fe4S4, the iron sulfide cluster, and let's take a realistic formulation of this molecule with a correlation consistent basis set. So to model that on a quantum computer, you will need 72 qubits and 6.7 million of Pauli operators. So if we even hope to measure the energy of this thing just once, well, the runtime to measure this at the current clock speed that we have for our quantum processors is like 3 million years. So this is something that's just not feasible with VQE with today. So in this talk, I'd like to address these two questions. The first one is, can we simulate realistic quantum models of nature before we have fault-tolerant quantum computers? So things like that molecule that I've shown you before. The second one is, can we simulate them, or can we simulate grounds? Can we address ground state problems with provable convergence before pre-fault-tolerant quantum computers get here? Well, let's see the first question. So if you, again, take that Fe4S4 model, and so it takes 3 million years to be run on VQE. Also, if, by the way, if we have the fault-tolerant quantum computer, it will take 13 days. So this is an estimation done with the surface code, 13 days and 4 million qubits. This estimation actually gets better with the new codes that we're considering at IBM, but still substantial amount of resources. And then what I'm gonna talk about in the following, I'm gonna show you that we did actually simulate this molecule, and the total runtime was 2 hours. And to tackle this problem, we used what we call quantum-centric supercomputing. And what we mean here is basically we are thinking of hybrid quantum classical workflows where this kind of workflows enable the execution of these use cases for quantum computers just using a few large quantum circuits, which is the best thing that we can do with the devices that we have today. We can't really run the zillions of circuits required to do this molecule on VQE, right? So we have to think of workflows that get there only by executing a few circuits. And this is what I'm going to talk about in the first part of this talk.
Antonio, I have a question. So is this 2 hours both quantum computing time and the HPC, or just on the quantum computer?
2 hours is the total runtime.
Okay. Okay, thank you.
All right, so this is how the workflow works. This is how it looks like. This workflow, we call it sample-based quantum diagonalization. So the idea is that, again, as I said, this is a quantum diagonalization method. So we're using quantum computers to address a ground state problem. And it's sample-based because we're not going to compute expectation values of local observables on a quantum computer, but we're going to use information coming from individual samples and process that classically. Right? So the way it works is we prepare on a quantum computer a wave function psi, which we believe is a good approximation of the ground state that we are targeting. I'm going to tell you in a few slides what's Psi for quantum chemistry problems. After we prepare Psi, we sample from Psi a bunch of times, and we get, we build this data set X tilde. And this data set X tilde goes through, so now at this point, once we took these measurements, the role of quantum computation is done. And, we post-process these measurements. We parse them through a step which we call configuration recovery, which is basically an error mitigation step. So what we do is we try to undo some of the errors that have occurred in these bit strings with information coming from the ground state itself, right? So this is a self-consistent loop. So basically, like roughly what we are doing is we are trying to flip back if we observe that those bit strings don't meet some symmetries of the system, then we try to flip the individual strings back according to some mean field properties, right? So we check the mean occupation of for a given qubit, and we try to flip that qubit back to that mean occupation if we detect that bit string has an error. After we do that, we obtain a what we call recovered set of configuration. And then, so this recovered set of configuration, we subsample it by frequency in batches. And for every one of these batches, we project and diagonalize on a classical computer the target Hamiltonian against these subspaces. So if you are familiar with selected configuration interaction methods for that people use in chemistry very often, what we're doing here is we're running a selected configuration interaction methods with samples from a quantum computer. So we're using the quantum computer to identify what are the important parts of the Hilbert space that we should look at and try to diagonalize our target Hamiltonian on. Maybe, is there questions on this workflow? I'll have one more slide later on this, but maybe there's a question at this level.
No, we're good.
Okay, so the circuit that we are using to prepare our approximation of the ground state function is, so we call these LUCJ circuits. An LUCJ circuit is basically a mid-ground between something that is hardware efficient, right? So an hardware efficient ansatz, and something that is more physically motivated, like the unitary couple cluster single and double circuits, right? Which were studied by chemists and people are trying to understand the power of these circuits for modeling ground state of molecules, and they look pretty promising. So the idea is to take a unitary couple cluster single and doubles ansatz, which is this one, but this one will be too deep to run on the quantum computers that we have today. So what we do is we approximate this ansatz by by interleaving quantum gates that perform Givens rotations. So this operator here, and the Jastrow terms, right? So ZZ gates, and then gates that, but basically it's layers of free fermionic interactions and some ZZ gates. And so this is how the circuits look like. This is the quantum circuit for our 52 qubits an N2 simulation. So you see you have the 2 layers of Givens rotation that sandwich a Jastrow layer here. And the first layer of Givens rotations is different from the second one because we're simplifying some gates, because we're taking into account that we start from the Hartree-Fock state. Okay, so that was the circuit. And then I'd like to spend some words, like to tell you why this is working so well. And I'm going to show you the data after. But what we're doing is extremely well. First of all, of course, we were solving the issue of measuring all those 6 million Pauli operators because we're shipping that problem to a classical computer, right? So remember, we're only using a quantum computer to draw samples, and then the rest is handled by classical. So the construction of the energy is done with classical computers at machine precision. So there's no issue with the number of shots there. And the quantum computer is used to identify good sections, good parts of the Hilbert space to look at. Okay, but then there is one more nice thing, which is this workflow is extremely robust to noise. So let me try to explain that with an example. Suppose that I have a 4-qubit system. I have a very simple ground truth for my 4-qubit system, which is this one here. All right, and then suppose that I have prepared my quantum computer a wave function that I believe I have some belief that it's a good approximation of this ground truth down here. Okay, and I draw like 3 samples from that wave function. These are the samples, A, B, and C. Okay, 2 samples, I nailed them, right? So A and C are exactly the bit strings that I need to build my ground state. And the third bit string, I don't need this. So this may be the third bit string. It's because I have quantum noise in my system, right? So maybe it's a noisy bit string, or maybe I wasn't that good in approximating building a circuit that approximate this ground truth. I don't know, but I have a bad bit string. Now what happens is if I project and diagonalize the Hamiltonian, which has this ground truth as the ground state, what I'm going to have is, what I'm going to get in output is the linear combination between these 3 bit strings, which has the least energy against that Hamiltonian. And guess what? That linear combination is going to be? It's going to be exactly this ground truth here. So the fact that I'm diagonalizing this classically in a subspace at the bit string level, it's going to, basically, this is going to assign a 0 probability to this bit string B. So now you understand why this is so robust to noise, right? So it doesn't, if you extrapolate this argument to the case that we have many black bit strings, many Bs, it's not going to matter. I can have like 1 million more noisy bit strings here, or bit strings that I don't need. As long as I have my 2 green ones, I'm always going to get the same answer at machine precision. So all those faulty bit strings are going to be assigned 0 weight. So another way to look at this is that we are paying a classical energy price. So we are diagonalizing the Hamiltonian classically, and the price that we are paying it depends on how much noise do I have in my quantum system. So the price that I'm paying depends on how many black bit strings I have. So how much noise I have in my quantum system, or how good I was in trying to nail this ground truth here. Right. So this nice trade-off between quantum and classical computational resources here. The better my quantum computer is, the less I have to use, the less powerful of a classical computer I have to use to do this calculation. Okay, and so now you understand the principle why, behind this workflow, like why it works so well. And let me just flash the results that we got. This was last year in collaboration with Riken and University of Colorado. So we have 3 sets of results. The first one, we have shown the bond breaking of the N2 molecule on a correlation consistent basis set. So this was an experiment done on 52 qubits. And here we show that data from a quantum computer can qualitatively capture the dissociation of this molecule. The second set of experiment, this is the this is the experiments that show the best precision that we got so far. So this is another iron sulfide cluster, Fe2S2. And this time what we did with the quantum data, we did an energy variance extrapolation, which is something that's done routinely by computational chemists and condensed matter physicists. So what you do basically, for every one of these quantum points, which are the dots in this scatter plot, we compute the energy and the variance. So these dots have different colors, and darker colors mean that we have used more determinants, so more samples from a quantum computer to build that wave function and to build that energy. In fact, darker point correspond to lower energy and lower variances in this block, right? So we're going, as the points get darker, we're going towards better approximation of that ground state. But one can also show with a simple perturbative argument that if I'm sampling from, if I have a tool with a knob, in this case, it's the, it's the number of determinants that we're using, the number of samples. If I'm sampling from something that's very close to the ground state, I'm gonna observe a linear arrangement in the energy variance plane as a function of that parameter that gets me to better approximations of that ground state. And this is true for classical methods, right? So people see this with the DMRG, the dimension of the DMRG, or again, number of determinants for SEI methods, and we see it also with this quantum method, right? So we use more quantum measurements, energies get better. And also, what we observed, it was actually, we start from relatively lower number of points, which are these yellow dots here, and we increased the number of determinants, and then we saw that the energy was going down, like according to a linear arrangement. And at some point, we observed these jumps, right? And then the jumps, it means that we're actually capturing the different eigenstates for this system. And the lowest energy eigenstate that we captured actually agrees with DMRG calculations, which are the state of the art for this system. So this is the most precise calculation of quantum chemistry done on a quantum computer. This was an experiment on 45 qubits. So again, it's a realistic formulation of this iron sulfide here. The last set of experiments, it was that Fe4S4 molecule that I showed you at the beginning, the one with 6 million Pauli operators. And here in this case, we show that there is, even at this problem sizes and circuit depths, I think the circuits here are thousands of gates. I think we're talking 3.5K 2-qubit gates. We see that there's still a signal coming out of the quantum computer. We don't do as well as for Fe2S2, but still a quantum signal is there. And so you see that these dots here are still arranged on a line, and they're better than the R3 Fock state, and are way better than these pentagons here, which is what we get if we just do sampling uniformly at random from a good section of the Hilbert space. Right, so summarizing, on the left, quantum qualitatively captured this dissociation. In the middle, this is the most precise calculation done for, and large-scale precise calculation done on a quantum computer. And on the right, here we're pushing the limits of these methods, okay? And we're still seeing that there is a signal of these problem sizes. Okay, so this is, I guess I already told you about this, right? So again, linear arrangements, signals that we are sampling from an eigenstate, and this is the system size at this point for this system here. So we call this chemistry beyond exact solutions. So okay, this might be a bit cheeky maybe, but the point is that the idea that we wanted to convey is the system sizes that we are addressing, they're not in reach of exact classical diagonalization methods. In fact, to the best of our knowledge, this system in red is the classical state of the art for exact diagonalization, and the system that I told you about, FE4S4, is like orders of magnitude bigger. In fact, it's even bigger than the storage of Fugaku. So we are targeting systems that are realistic formulation for these problems, and are not for which exact solutions don't exist. I'm going to tell you about this last row here, which is the collaboration that we did with Oak Ridge this year.
Antonio, can I ask a question really quick?
Yes.
Is delta H just H squared?
Yes.
So in this case, you have like a trillion
It's the
polystrings?
It's the variance.
Does this mean you have to calculate a trillion polystrings in your ground state that you compute?
Yeah, I guess. Yeah, you have to do H squared. Yeah, it's way more expensive calculation for sure. Yeah.
Okay, but still doable.
Yes. I don't know if it's yeah, but that's the idea. It's H squared. Okay, so how does a quantum advantage look like within this workflow, this formulation? Okay. So we will get quantum advantage if a quantum circuit is better at selecting determinants to use in that classical diagonalization step than existing classical methods. So the first thing that we wanted to show, the first thing that we are showing here is that quantum circuits that can sample more efficiently than SEI methods, they exist. Okay, at least this is the first step to go towards a quantum advantage for this class of methods. Okay, so how do we show the existence of this? First, we run a classical selected CI method, which is, in this case, we use the heat back configuration interaction method. And the circles that you see in this plot, they're the different steps of the classical selected CI method. And so you see that on the x-axis here, you have the subspace dimensions. So how many determinants, how many bit strings I'm using to diagonalize my Hamiltonian. Now, the y-axis, you see the energy of that system going down, right, as I use more bit strings. And it's fine. And the different colors it doesn't matter that much. It's just like different thresholds for that classical method. We can just like focus on one of these plots and just talk about that. This one, for example. So the first question that we asked is, okay, so I have this classical method that spits out a bunch of bit strings. And the more bit strings this classical method spits out, of course, the lower the energy gets. But the first question is does it exist? Like, is this classical method performing a perfect sampling? Which means, suppose that I have a budget against a bit string budget and a budget of number of determinants against which I want to diagonalize my Hamiltonian. So to say it's 50 million determinants. And now the first question is this classical method giving me absolutely the best 50 million determinants that I can possibly choose to get the lowest energy? And the answer to that question is no. So the first thing that we show is that indeed there's a better selection of 50 or whatever millions determinants than the ones that these classical methods are giving us. that gets a lower energy with the same number of determinants. And this is a brute force calculation. We're just showing that this is an existence argument. Okay, so we show that that sampling is not optimal, and the optimal sampling is this brown line here. Okay, so now that we have this optimal sampling, we take with a brute force calculation, we take those optimal determinants, so those optimal 50 million determinants or whatever, and we train a quantum circuit minimizing some statistical divergence against that optimal set of determinants. And what we find is that these quantum circuits, the LUCJ circuits, in fact, at very low depths, actually I was a bit surprised by this, at very low depths can sample very closely to that brown line. So again, so if someone came and gave me that quantum circuit, at the zero cost, then I would say this is quantum advantage, because that quantum circuit is giving me a more efficient sampling than a classical method. Okay, so this is an existence argument. Now, what we have to show is how do we find those circuits efficiently? But for now, we have shown that these circuits exist. And this is it's a non-trivial statement. One way I see this is that this is a quantum version of QAOA, in the sense that the target problem that we're trying to solve, it's not a max-cut problem, but it's a quantum problem. But the spirit is the same. So we're using a bunch of bit strings, so the solution can be stored in classical memory. And that energy of that solution can be checked classically. And as the same thing as QAOA, we're using a quantum computer to determine what are the bit strings, the best bit strings to solve that problem. Except that I have a higher hope for this class of problems to show quantum advantage than QAOA, because these problems are quantum in nature. But also, unlike QAOA, if you give me as a solution for QAOA, then reconstructing the circuit that gives me that solution is a very easy task. I only need a bunch of X gates in just one bit string. But in this case, it's highly non-trivial to show that there is a circuit that can encode that solution. So this is what we did here. Is there questions on this?
Somebody call me.
No questions?
No.
Okay, now the second point. Something that we liked about phase estimation, and something that everyone likes about phase estimation, and I would argue the reason why phase estimation is chosen as the prototypical benchmark algorithm for so many applications. Everyone counts their gates against phase estimation, is because it has provable convergence. So it's the best thing that we have, the best tool that we have to show that quantum computers will succeed at the ground state problem. Okay, then my second question is, can we have something that has kind of like similar convergence to phase estimation before pre-fault tolerant quantum computers? All right, so to answer this question, I'm gonna talk about what we call Krylov quantum diagonalization, which is just a quantum version of a classical power method, right? And every variant that you can imagine, but this is a quantum version. So what we do is we take a reference state, just as classical power method, and we apply, so in a classical version of this, you would apply powers of your system Hamiltonian to that reference state, and then do something with the outcome. And in this case, we apply real-time evolutions to a reference state loaded on quantum computers. So unlike classical power methods or Creel methods or Lanczos methods, this step is efficient for quantum computers. It's efficient as a function of the power, as a function of B, these powers. Okay, and then one builds these states on a quantum computer and computes the matrix elements of H, and also these states are not orthogonal, so we also need an overlap matrix. And then one solves on a classical computer a generalized eigenvalue problem in this subspace. Same thing as we do with classical methods, except this time we're using a quantum computer to build, to project these two matrices. Okay? And it turns out this works fairly well in practice. This is an experiment that we did with University of Tokyo last year. The system that we targeted was this Heisenberg Hamiltonian. And this is the results that we get. K here is the fixed number of particle sector that we're working in for this Hamiltonian. So K1 is easier than K3, easier than K5. But you see that the energy per site for this Heisenberg model, it goes down as a function of the subspace dimension D, which is how many Krylov states we're using to diagonalize this target Hamiltonian. The nice thing about these algorithms is that they have a convergence guarantee. So if I start, it's similar to phase estimation. So if I start from a reference state, which has a polynomial overlap, gamma 0, with my target ground state, and if my energy spectrum is well behaved enough, then I am guaranteed to get an energy error on my final approximate energy error is going to be this formula. It's going to go according to this formula here. There's actually this one term missing in this formula, which is my shot noise, right? So basically, the convergence is efficient. So the convergence is going to go exponentially down as a function of the Krylov dimension D, and it's going to be bounded at the end by, modulated by the overlap that I have in my true ground state. And then, there's a term here, which is the shot noise. Of course, since we are estimating those matrix elements with a shot noise, my error is going to be bounded by shot noise. But you see that we observe this, the behavior described by this formula in these plots here, right? So the energy goes exponentially down as a function of D, and then it saturates because that's the precision with which I'm measuring things on my quantum computer. All right, so you see there is still an issue here, which is, again, the shot noise. And then one other issue is that I have to compute these expectation values, which is not easy on a quantum computer. One has to do the observable-based error mitigation methods, which they depend on how precisely I can measure things on my quantum computer. So, okay, so now let's combine the two things together. The thing that I show you at the beginning, which was what we call sample-based quantum diagonalization, but let's sample this time from Krylov states, right? So we kind of have the best of both worlds. So instead of coming up with an ansatz for my ground state that I have to sample from, now I'm going to sample from these time-evolved states. And if you sit down and work through some algebra, you realize that the convergence properties resist the fact that now we're not classically diagonalizing that subspace built with expectation values anymore, but now we're working on a subspace based on individual samples, right? But you can still show that if we do this, this thing converges with a runtime, which is given by this expression here. So this is the total number of shots that I need to get to a ground state energy with epsilon error with probability 1 minus eta. And of course, this depends on the overlap of my initial ground state with the ground truth. One thing, since we're working with a sample-based approach, now we require sparsity in that ground state. So this stands true if the ground state that I'm trying to approximate is sparse, right? Otherwise, I would need, otherwise it would be unheuristic. It's hard to prove. We can still try it, but the proof holds if I start from a reference state that has a polynomial overlap with the ground state, and my target ground state is sparse. If I have all these things, then I'm going to converge to the ground state efficiently. And this is the second work, I guess the third work that I wanted to talk to you about, done in collaboration with Oak Ridge. But we have shown that actually this workflow where we combine the sample-based approach and Credo works extremely well. What we tried it against a single impurity Anderson model. Actually, now we are trying to go for more impurities. And we showed that, here, the agreement is excellent between DMRG simulations and SKQD, right? The sample-based Krylov approach. So this works really well. And again, I like to stress that this is it's a method that we can run on pre-fault-tolerant quantum computers, but share some desirable properties of fault-tolerant methods like phase estimation. Now here the same data, and also you can see how that the energy is also doing very well against CCSD. And this is a big system. This is 85 qubits, and the largest Krylov state that we run for this system had 6,000 gates. Right, so summarizing, the take-home message is, I told you about two algorithms, right? So we call them SQD and SKQD. So sample-based and sample-based with a Krylov, sample-basing from Krylov states, right? So the circuits that we have to run for these two methods, for SQD, remember, we need an ansatz to get to that ground state. For SKQD, the ansatz is swapped by time dynamics. So this also means that we cannot use SKQD for chemistry, right? At least not in this formulation, because we have to run time dynamics for that system to get to the ground state. So bottom line, SQD, with an ansatz, it's very well suited for use cases like chemistry. But if I had a lattice model, I think running SKQD is almost like a no-brainer. Like if I can do time evolution for my for a small phase of my system, or for like some phase for my system, I would definitely run this SKQD business. Again, there's no convergence proof for SQD case, but we do have a convergence proof in this case with efficient convergence with assumption of sparsity and overlap of a reference state with the true ground state. All right, so this is a super high level. I hope it was clear. And I just wanted to say that all the stuff we're working on it with our HPC partners. And, we are trying to define the future of quantum data centers with, all these organizations, especially the chemistry use cases. Cleveland Clinic is all on running their use cases against using these algorithms to run against the use cases. Lockheed Martin, same thing. And the two works that I told you about were with Rick and Oak Ridge. But this was my last slide. And again, thanks for your attention.
Thank you, Antonio. Any questions? Yeah.
Yeah. Thank you for the very nice talk. So I have two questions. One is about the Krylov quantum circuit you showed us. Like in the construction, you need to evaluate, for example, the off-diagonal matrix element of the Hamiltonian, which in principle can be complex. I just don't get how you get the complex fit. Yeah, right. How do you get that part correctly?
I think my video froze. Can you hear me?
Yeah, we can hear you.
Yeah, we can hear you.
I mean, this is just a standard Hadamard test, right? But actually, in the paper, actually, we didn't run a. Let's see if I can fix the video. In the paper, we didn't run the actual Hadamard tests. There's tricks that you can play if you have some symmetries in your system. You can go around that because the Hadamard test is expensive because you have to run controlled unitary operations. But if you know that your system has some symmetries, then you can play tricks and not do those controlled unitary operations. And those tricks involve preparing in superposition your target reference state and another state which lives in a different symmetry sector than what you're interested in. If you can do that, then you can avoid those nasty control unitaries for the Hadamard test. But again, this is the OG, the original Krylov business, which is not. It takes a lot to run this thing. Like we did these experiments, but this took a while to run it on a quantum computer because again, getting these expectation values, these off-diagonal matrix elements is not easy. But the sample-based version of this, it's very robust and easy to run. And the argument is this one, right? The sample-based stuff is really robust to noise.
Thank you. Yeah, I have another question about the first part because this is sample-based on that kind of ground state estimation. Say, for example, I run the quantum circuit 10,000 times. Some basic states appeared 1,000 times, some appear 50 times. But then when you diagonalize the kind of effective Hamiltonian, you kind of treat this type of two states equally. There is no penalty for the states that showed up less frequently. Is that right?
That's a great question. Yes, that's exactly right. So as long as you sample the right states once, you're good. Mm-hmm. So this is okay. This is something that I struggle to convince people of, but that's fine. That's how these algorithms work. So I only have to get in this diagonalization step, all the relevant bit strings once. If I sample, if I sample the interesting stuff more than once, it's a bit of a waste. And in some cases, sampling from the exact ground state is not the optimal thing to do. So, like suppose that for example, your ground state is like something like very peak on a few states, and then it has has polynomial size support, but then has other states with a very small probability, right? But I want to get those states with small probability. So what's the optimal distribution to sample from if I want to get all those states in once? it's
It's a
not,
uniform.
sorry?
Sorry, I just mean it's a uniform.
Yeah, exactly.
Right.
Uniform or something like that. It's something close to the uniform, but it's not the grounds. So this is a very important point that also if we were to optimize, like with the work that we did with Weekend, we didn't close an optimization loop here. But if we had to optimize this loop, the optimal psi that we would get to it probably will look different from the ground state. But still, you can get a perfect answer, the perfect ground state, sampling from upside that it's not the ground state. So it's very robust.
Yeah, okay, I get it. Yeah.
Yeah.
All right, thank you so much.
Any
Thanks.
question from the loop people?
Okay.
I have a couple of questions.
Okay, go ahead.
Okay, yeah, thank you for the great talk, Antonio. I guess a follow-up question to Xiaojun's. So let's say you say like a better distribution would be if the probability was more uniform. Wouldn't this affect this clustering step here, where you're flipping the bits to be closer to the mean value? But I'm guessing you want the mean value to be closer to whatever the actual ground state mean value is, or how does this step actually work?
Yeah, thanks. That's a good question too. Well, first of all, I haven't said that uniform distribution is always the optimal. I've said that I can imagine some cases where the uniform distribution is very good. In general, nobody knows what's the best distribution. So these flips, no, this does not depend on this. This is a self-consistent loop that I get after I diagonalize, I classically diagonalize my Hamiltonian the first time. So these probabilities, the mean field probabilities are not coming from a quantum computer, they're coming from the first classical diagonalization step. So again, it doesn't matter how frequently I sample things from my quantum computer. All that matters after the quantum computer is done is the support of the distribution it has sampled from. The frequency, there's nothing about the quantum frequency once we shift to classical.
Okay, yeah, that makes sense. And then the other question, you mentioned that for these sample-based techniques, sparsity in the wave function is quite important to have good convergence. Do you think it would be useful to consider a family of Hamiltonians related by a unitary transformation, and then trying to find the ground state energy of each one of those Hamiltonians, so you can try to find the optimal basis where your ground state is the most sparse?
Absolutely, yes, we're thinking about that for sure. Of course, yeah, that's if you're able to find bases for which your problem looks more sparse, all of this stuff is going to work better. It's a very hard question. It's a very hard question, but yeah, people can think about that for sure.
But I guess like as a variational approach, you could just try a bunch of bases, and the one with the lowest energy is going to be the best one.
Yes.
Yeah.
Yes. You can even mix bases. Like you don't have to sample from one basis. You can have different size in many bases. Yeah, thanks for the question.
Any other questions?
Maybe I
Okay,
ask a short one. So yeah, just in this setup, the last step, like lowest energy and average occupancy, and then there's another arrow pointing back to the configuration recovery. Can you elaborate this arrow a bit more?
Yeah, okay. So this configuration recovery step is something that we do. This works very well for chemistry. I'm not sure about other systems, but so the idea is that it's the following. so, chemistry wave functions are like many chemistry wave functions are, the mean field occupations are a lot of chemistry wave functions are very close to have like a mean field character, right? So if they have that mean field character, and suddenly I get a sample from my quantum computer which is very far from that mean field, then probably have to like flip the most likely error that happened on my quantum computer is probably an error that took me from a bit string, which was the closest to whatever my mean field state is, to something like very far from that. So that's the spirit of this configuration recovery. Now, of course, yeah, this works very well if you have a mean field character, but if you can always throw at things and then throw it at things and see if it works well. Or you can like twist it. Maybe if you have you can. I can imagine that one can design more complex version of this configuration recovery. For example, if you have a multi-reference character state in your ground state, maybe you can do something like a bimodal distribution, and you can flip maybe around 2 reference states or something like that. It's kind of like an error mitigation based on the physics of the problem.
Yeah, okay. Like we know it's a mean field, so we can use that information to see like.
Yeah, or I think you can modify this for something that doesn't have a mean field character. As long as you can identify what are your clusters against which you want to flip these bit strings, you can do that too. I think at some point, actually, we were trying to implement a machine learning clustering algorithm, like to find the centroids around which to flip the bit strings. But then, yeah, we dropped it. Maybe we pick it up later.
Yeah, and the first question. If not, let's thank Antonio again.
Thank you. Thanks.